Yeah.
So just fly by the seat of your pants, my man.
So it
Just
actually,
what?
I have a tablet right here, so I can draw with like neater handwriting, I think.
Well,
Is it?
splendid.
I can't. Okay. Um. Hmm.
Well, let me ask you this. Whenever we do a graph, is there ever a time where you look at it and you just say, well, I know that the thing has to be such and such at such and such? Can't we say that about what would be the force acting on this puck at a certain place?
Uh, 0. It's gonna be 0, 0, 0.
Excellent. Good. That's how you start.
Okay.
Now take it to the other extreme. Where are we going to go with this?
It'll be like really high to the negative as you go negative. No. It'll be a pot like it'll be
Right.
so it'll look like that kind of.
I think I missed it. I didn't see anything drawn. There we go. Exactly. And now
Okay.
go the other way.
And then it's gonna look like that.
Yep.
Okay.
So the whole idea is that if you see field lines and they're coming closer and closer together, then you know that the force has to get bigger and bigger, and it will be asymptotic here. And if you wanted to go outside, we could, but we don't have to do that. This is good enough. Just inside is good. Now I want to zoom in on this. Now I did not put this on your handout, but I got to thinking maybe we ought to talk about it. In the next part of the problem, I tell you that this thing's got a slope. But is there a reason why it has a slope? Could it have 0 slope? Is that a possibility?
Yeah, why not?
Because there's actually something that you know about this. I'm going to make the problem simpler. This is often what we do in physics. If you don't understand a complicated thing, make it simpler and it might help. Here's an example. What if I had a negative charge here, right here, and over here I have another negative charge? Would we be able to make a graph of F versus X based on these two charges for another charge in the middle? If we move this charge over this way, you know that's going to push it back because it's negative. And if you move it this way, it's going to push it to the left because it's negative, right? But let's eliminate one of them for a moment and ask ourselves, what would the graph look like just for this charge? Does everybody see that? Uh-oh. Did I lose you guys? I'm drawing it in like this. That would be the graph of force versus X for this guy sitting right here. Okay, this is getting creepy. Is there anybody still there?
Yeah.
Yeah.
Got it. Do you understand what I just did then? It's 1 over X squared, isn't it?
Yeah.
Okay. Now let's just turn this guy on. Forget about this guy and just turn him on. That graph will look like this.
Okay.
So what's the sum of those graphs? You're going to add them up, and yeah, it'll be 0 in the middle, but this will definitely have a slope here, won't it? This will definitely have a slope here, won't it? So when you add them up, guess what? You got a slope. Do you like that argument?
Okay.
I'm building the argument on things that you've already done before. In other words, you can make an approximation without having to worry about doing some big complicated derivation. All right, my graph isn't so good. All right, so now this slope in the next part is given as what value?
-10 newtons per meter.
Was that you, Bryson?
Yeah.
Thank you for talking to me. It's very lonely on this side of the screen. You see, the funny thing is I picture you guys all being together.
Like in the class?
Well, somewhere, like you're hanging out at somebody's TV room or something, and I'm in the house all alone here. Okay, what a
Yeah, I'm right by
sad,
Dayton.
pathetic visualization. So,
Cody wasn't invited.
I know, sorry. Okay, the puck is given an initial velocity of 10 meters per second in the positive x direction. Can you figure out how to calculate the x max? What does this mean that we're going to assume that the radius of the ring is very large?
That the
The other side doesn't affect it as
slope
much.
is going to be essentially constant.
What the hell was that? Yes, if I say the ring is really large, we're not going to worry about getting close to here. That means this slope is going to be constant, okay? That's what we're working on.
Mm-hmm.
So if we do that, can you make an assumption here about how to figure out how far x goes? It shouldn't be too hard now.
EE is equal to 1/2 kx
Yeah,
Where-
yeah, I think that's how I would do it.
With
What-
energy.
What happened to my thing here? Yeah, I would say the energy initial equals energy final. Now, some of you are sending me work, and it doesn't always start with the basics. Do you remember the last sheet you sent me, and it had to do with a collision? And
Mhm.
I said, you want to tell somebody what you're doing. And I had on there something like 1, shift the frame of reference to the center of mass. 2, the velocity of approach equals the velocity of recession. 3, shift the frame of reference back to the original problem frame of reference. Now, those are the 3 things I wrote. Now, Shivam, are you there?
Yes.
I loved what you wrote. Do you mind me telling everybody?
I don't mind.
This is what he wrote on the top of his paper up there. Right at the top of all those calculations, he wrote 3 steps. And then he just did all the numbers. So I don't think there's anything in physics that says, if you can find it in a book that says it's 3 steps. But I want you to write something that a grader can actually say, oh, that's what he's doing. He's shifting the frame of reference to the center of mass. So I got a good chuckle out of that. I hope you can find some humor in it too.
Mhm.
Now, what is the energy initial? Correct? This is just like from the last problem, isn't it? So how about we all calculate how far this thing's going to go right now? I forgot the mass. Got it right here. The mass is 1.8 kilograms, right? What did you guys get?
4.24 meters.
That's what I'm getting. Now, I'm not saying this is something that's going to happen in our laboratory. I just made up numbers. I knew that it wasn't going to work out, but I got tired of messing with it, and I don't care. So are you all right with this? I mean, no one's going to have a 2.5 Coulomb charge on a particle either, so it's totally unrealistic. Does anybody have any questions on what we've just done? Okay, kids. This problem is going to get interesting. Trust me. Tell me what we're going to do for a free body diagram here. Oh. Oh, why won't you? I'm going to have to call on a kid, won't I?
Dean Chumash.
Who is that?
Addis.
Me.
All right, Addis. Tell me what to do.
Oh, MG. I thought my mic was not muted.
There we go. There's our MG.
Popcorn Dan.
I got to tell you something funny. You know, on that last sheet that you guys sent me, the last thing that I was just talking about, didn't I tell everybody that you have to label your free body diagram, even though I didn't complete my free body diagram? You're not going to believe this. I still have kids handing me in arrows with no labels. You can't do that. Now, won't we have the same thing over here? Yes?
Yeah.
Thank you. Put those labels here. What's going to be the difference in these two diagrams? There's something missing. Remember, it's a side view.
FE.
Yep. You need a force here. And what about over here?
Smaller.
Yep. So I kind of, like I said before, will you lose points if you don't draw it to scale or roughly to scale? I don't know. They'll probably tell you that, yeah, if you had to do that or not. Okay, so everybody gets the idea. The further away you are from the equilibrium position, the bigger that restoring force is. Good?
Mhm.
How are we going to find the period for this thing? Somebody talk. Adriel, you always will talk to me, won't you?
I don't know the answer, so.
It's the formula for the period of a...
Square root. M
Oh,
over
then
K.
square root m over k.
Yeah. Look, there's only a few big concepts in mechanics that you really need to worry about. You could probably count them on two hands, total, maybe one hand. Simple harmonic motion is definitely one of them, okay? So get used to this. 2 pi square root of m over k. So let's go calculate it. What'd you get, kids?
2.67 seconds.
Yep. And at this point, you might be saying, gosh, damn, can't he come up with something different? It's going to happen, just not right now. So you're writing this stuff down, I assume, right?
Yeah.
Because we might want to compare it later. So the initial velocity is now 20 meters per second. Now, we already had a thing a couple days ago. You could probably just skip it. If you double the velocity, what will happen to the maximum displacement?
It will double.
Yes. Do you remember that? The kinetic energy and the potential energy both have a variable that's squared in it. The x squared and the v squared. So, hey, you double one, you double the other. So what is this number going to be?
8.48.
Is that cool, huh? Now, here's the part where kids do stupid things. They're going to sit there and calculate the period.
It's the same.
It's the same period, folks. What is it? Right? Now, on an AP exam, if something like this should happen, you don't have to waste your time. You could just write same period, amplitude doesn't matter, and then move on. Okay. It might be quicker to do the calculation. I don't know. Now, you know how they always like to make us think about lab work? That's what they're going to want to do. What if you were given 2 photo gates and they're connected to a timer? Each can start or stop the timer when the puck passes through the gate. If the puck passes through the gate a second time, the timer will start again from where it left off. So if it passes through a second time, it's not going to do you any good. You may use one or both photo gates, and you may position the puck at any initial location. What would you do to measure the period? Now, you want to think about that for a second? I'm going to draw a diagram here because I'm supposed to. Whoops, whoops, whoops. I'll use this thing. Here's the ring of charge. Hey, I thought that was supposed to be completely circular. I pressed the The shift key, I thought, well, whatever. Okay. Now I need some suggestions from people. You know what? I got to see who's here. Tell me, Mason is not here, is he? I didn't see him join. How about Haresh? Are you here? Hisham? Jordan Petzold. Holy jeez. Shivansh. Shivam.
Yeah.
Adriel is here.
Yeah, I'm also here.
Okay.
Hello.
So I do have a few people who didn't make it. Dean did not get here. Thomas didn't get here. Abrar. And Shivansh. I didn't hear from Jordan Petzold and Hisham and Haresh. And
Yeah, I'm here.
who's here? Who's that?
Oh, I'm here too.
Haresh.
Haresh is here. And Hisham?
Yeah.
Okay, Jordan Petzold, still no? Okay. You know, I'm still getting used to this thing. Now, you know what I figure? People could still come on and not say anything for 45 minutes, you know? And then I'm going to mark them here. The hell with that. I want to hear from everybody. So where do you think that you would put a PhotoGate timer? Where would you want to put the hockey puck to get started? Where would you want to make its initial position?
The start, the origin.
That would be probably what most people would do.
Wouldn't it not move?
That's the question. You see, if you're doing a lab and you let it go from here, you're right. It's going to sit there. That means if you're going to try to test to measure the period, see, you got to measure the period. That means you're going to have to give it an initial velocity. How the hell are you going to know what initial velocity to give it?
Just put it at the side.
Yeah, I would put it at the side. Now, honestly, the other answer is you could give it any initial velocity you want. Why?
It's not going to affect the period.
Exactly. So you understand now, it all depends on how you express your answer to the grader. If you told him, I'm going to start it off at the equilibrium position, and then not tell him what you're doing, you're losing all the points. If you told him you're starting at the equilibrium position and giving it a velocity to the right, and you can say, because the criticism would be you won't be able to produce that velocity exactly, you have to say any velocity will do. Okay? Let's continue talking about starting it over here. What if we put it at the maximum displacement? Now, where do you put a PhotoGate or two PhotoGates so you can measure the period?
Put one at the center.
I would put one at the center. Whoops. And we'll do it kind of like in 3D here. Oh, little stinker. Okay, so this thing's going to come through, and whoever drew that, thank you. It's going to come through this thing. And now what? The timer starts.
Mm-hmm.
So, are we done? Is that all we have to say? Put the thing over here and let it go?
No, you have to put one at the original position too.
If you put one at the original position, it is extremely difficult to work with PhotoGates when you put it at the original position. Why? Because it'll keep triggering it as you start to use it. So you have to put it just a little bit above. Like you'd want to put that like maybe a half a centimeter in front. And then, okay, so let's say you did it this way. You're going to get it. Huh?
Could you put it at the maximum displacement on the other side?
I would do that. No, I won't. I'll get in trouble doing that too.
How
Hold
would
on.
you know where it is?
Let me just explain this first. So let's say you pull the hockey puck back just ever so slightly and let it go. It's going to come through here, start the timer, going to go through here and stop the timer. What would you want to tell the guy over here what you're doing with those numbers? You got one number, a time. What would you have to do?
Double the timer.
Double it? Come on, somebody
Cut
else
it in
kick
half.
in. What?
Times 4.
Cut it in half.
Not cut it in half.
Times 4 because
Times 4.
Each one's
Because
a quarter.
from here to here is only a quarter of the period. When it goes through, it stops, comes back, and then it's going to come all the way to here. That's a full cycle. So you're only getting the time for a quarter of a cycle. These are the kinds of questions that they ask on these open-ended things to get us to think about a lab. And I think this is a good discussion to have. Now, getting down to the nitty-gritty, this is not probably the best thing to do because, okay, you're going to have a hair trigger. They're probably not going to care. They'll be happy because they'll know you just have to tell them, make sure the hockey puck stays back just a little bit. I think you could do the lab with just one gate.
Mhm.
How?
Put it all the way at the end.
No, just leave it right here. Don't even bother with this one at all. Let go of the puck and what's going to happen?
it will go and then hit the gate, and then it goes to the other side and it comes back, and that would be 1/2 a period.
Right. Because the way these photo gates work, and we've used them in class, you've seen them used. When you trip it, the clock starts. When you trip it again, the clock stops. So I think this is the way to do it, probably the easiest way. One photo gate, let it go back and forth. Did you find that to be a little bit interesting of a discussion?
And it's optional how many you use, right? Like it tells you it doesn't matter how many.
Yes, and
Okay.
that is the well, you have 1 or 2 is what it says.
Gotcha. Okay.
And the ambiguity is intentional and it frustrates kids, but that's the way real life is. If they say, describe a lab, how you would measure something, who the hell, geez, the door's wide open, It's a scary thing because we're so used to having exactly defined problems where we plug numbers in. So let's say the other idea, I think Jordan Totten was suggesting that we put it over here. If this thing comes through, it's going to start the clock. When it gets to here, what's going to happen? Jordan Totten, where are you?
I'm here.
Okay, so when it gets to here, is it going to stop the clock?
Yeah, but then when it started again,
That's debatable, and it could start again. So could you picture the beam of light right here? So that the thing comes in and it leaves. It's not going to trigger again unless it passes all the way through and then back again. So yeah, if you're careful in your placement, it's going to be fine. If you place it a little too close and the puck goes through, when it comes back, the clock starts again and you're going to lose your data. These are minor points, okay? But I think that you could, the best answer is just the one, and I think that's kind of creative. But nonetheless, I thought that was interesting. Okay, now here comes a variability on this. What would you do to measure the maximum velocity? Now, Dan, hold on. I'm going to just let me erase this first.
All right.
Whoops. First, you want to tell me, where do you want to start the puck?
At the outside.
Yep, I'll start it at the maximum.
And then
Any
I would have a
ideas as to
gate-
where we should put a photo gate or two?
I would have a gate like right here near the equilibrium, and another one which is also near it, and
Yes.
you can see like that's
Yep.
D, and it'll give you a time, and V,
Yeah.
There you go.
Could you tell the grader what you're assuming about your method right here?
Velocity is constant.
Yep. Is that a reasonable approximation that you can make for this problem?
If the D is small, yeah, sorry.
Not only can you say if the D is small, I think you can also say that the force will be 0 in the middle, and it's not going to be that big on either side because of the graph. What do you think? Like, I'm not going to have a lot of acceleration here. That's my point. Because the force is so small. You dig?
Yep.
So they might
Uh-huh.
actually say, give two reasons why you give two approximations that you're going to make. Well, this would be one, that the D is small, you got to deal with that. And two, that the acceleration isn't going to be very big anyway. So that's cool. I hope you enjoyed my thought process on how to take a problem and make a little lab issue out of it. Now, this is the part where I think we're going to have to just think a little bit here. I don't want to just have everybody call out what's going to happen. The experiment is reset with the puck at the origin with an initial velocity of 20 meters per second in the x direction. This time, a magnetic field of 0.75 Tesla is directed down through the table. Holy smokes, what did Goodman do? We're going to have X's here, aren't we? I'm just going to put one X. So you know the field is going through this thing like this. This problem, I'm telling you, is so damn cool. Whoops, whoops, whoops. Didn't want to do that. Yeah. What is the charge? Holy jeez, did I grab the wrong thing? Can you tell me what the charge is on this puck?
Negative 2.5 coulombs.
Can you tell me what the initial velocity vector looks like?
It's to the right.
Can anybody here use their right-hand rule?
It'll curve upwards.
Yeah,
You- How many people got that thought process going here?
yeah. I agree with
You
that.
think that's cool?
Yeah.
There will be a magnetic force this way, won't there? And this thing is going to curve. The next question, though, is what's going to happen when it gets to here? Will there be a magnetic force on it?
Yes.
Yeah.
Why?
There's still a magnetic field.
Okay, but what do you need to have a magnetic force?
A velocity that is perpendicular.
Perpendicular.
And if this velocity is now this way, remember there's negative signs all around here. If this thing starts approaching this, what will this do to it? It's going to push back on it, won't it?
Mhm.
Yeah.
And it's going to have to come to a stop before it comes to here. Yes or no?
Mhm.
Well, then what do you think is going to happen then? Will there be a magnetic force on it if the velocity is zero?
No.
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 Now, you could argue more about this, about will the velocity really be zero, because this thing could curve and the normal force will be going up. But I'm looking at it down from the top, like a bird looking down on the lab table. At the equilibrium position, what would the free body diagram look like? Akil, are you there? Do you know, you're one of those kids that's, I hate to, call you out in public, but you're one of them. There's others that still want to put a velocity vector in your free body diagram. So don't do it anymore. Do you think that me talking to you now will help you remember not to do that? Thank you. I'm not trying to bust your chops, but hey, better now than when they go to grade the thing. So you know that at the equilibrium position, this thing was going to have a velocity this way, right? But you don't draw it. What do you draw?
FB.
That's right. You're going to write FB here. Is there another force vector that you need to put on here?
MG.
FE
Yeah, you
going
can't
down.
do it because you see that's going into the paper and we're not doing that. You get it?
FE going down.
I wouldn't put an FE on here. Why? Because you're at the equilibrium position. That's exactly why I've just asked this question. What is the electrostatic force when you're at the equilibrium position?
0.
So then that's all you're drawing. You dig?
Yeah.
Let's draw it over here now. What do you think's going to happen? Look, forget the whole thing curving upwards. Okay, well, let's imagine this thing now is closer to the edge. I'm going to draw it like this. Here's the edge. Uh-oh. Not what I wanted to do. I'm going to
Why
put
you said there was no MG again?
excuse me?
Is there no MG? You said it was going through.
Oh, look, this is a top view.
Oh,
Thank
top.
you.
Okay, yeah. So it'd be
so
going.
you could try to put it in there, but you're going to have to put like an X and then a dot to represent those two vectors. So whoever
Yeah.
just drew this, was that Adriel?
Maybe.
Thank you. So let's imagine that this thing has curved upwards and it's moving in this direction, but then it stops. Oh, a participant. Dan is back. Okay, I can't do it yet. Here we go. Whoops. Let's assume you thought the thing stops moving. If it does, then what force vector would you want to draw here?
FB.
Yep. Where FB? No, it stopped moving.
Wait.
FE, where would that go?
Going down.
In.
Straight down?
No.
Towards the center.
I think it would go this way.
Yeah.
I mean, if the curve is correct that Adriel drew, where the hell is my drawing thing? They keep changing that icon. I don't know. Anyway, if this is curved like this, then it's going to push it this way. Does anybody see that?
Yeah.
Now, look, I am trying to make the problems look different. You're not supposed to look at this and say, oh, yeah, we learned this already. It's all weird. Now, what about the velocity vector? If you thought this thing was curving and there was a velocity, watch my cursor. If the velocity was curving around like that, well, then where would you put an FB now if it was curving up like this?
In the direction of FE.
Yeah, it would also go this way. Both of those forces could be there. It all depends on your assumption about what you're saying this velocity is going to be like. I'm not saying that you're going to have to know this. I'm just saying if you can explain what's going on, great. I'm not you can't expect a kid to know exactly what this trajectory will be. Not with what we've done here. But either way, you state your assumption and you draw the force vector accordingly. And you'll get points. Remember, you're not trying to get all the points. Just start racking them up little by little. Okay, now, this is a really cool question. Find the time for the puck to return to the equilibrium position.
It
Can we make
has
an
to be the
assumption?
same as
Yes.
the period.
It's
Is that-
amazing.
B can't do any work.
Right.
Yeah. Okay.
Now, listen, this is the craziest thing. I made this question up because that's exactly what the reasoning I wanted people to use was that if the B is going to do anything to this thing, it might curve it around a little bit, but it's still going to take the same amount of time to come back. We're going to watch it on the computer program and you're going to see how cool this is. So I would have put down the same amount of time. But right now, let's sketch these energy graphs, and then we're going to get to the computer program, and you're going to say, golly gee whiz, Mr. Science, that's cool. Nobody's talking, huh? Let's go back to the simplest thing possible. Forget the magnetic field. Just imagine this thing is going to end up over here. Then it comes here. Then it goes here. Then it goes here. What would the PE graph look like? Somebody draw it, whoever can draw. Whoa, too many lines. How can that happen? Just do one.
Wait, what are we drawing?
So potential energy. Is there any potential energy at time 0? So yeah, the potential energy is going to go up. It's going to reach here. Now what? Yeah. Now what?
Back
Keep
up.
on going. Can somebody continue this graph? Okay. I was wondering if somebody was going to do that. Can you have, if this is 0 PE and I go to the right, I'm going to gain PE. If I go to the left, what's going to happen?
You'll lose PE.
I'm going to gain.
Still?
Yeah, here's how it works. Watch. Here is a force versus, when you see this, you're going to say, oh yeah, I knew that. When the force graph looks like this, you need to make a potential energy graph. If this is PE.
Mm-hmm.
Is everybody watching this, just not me and Dan?
Yeah.
Yeah.
The potential energy graph is going to look like this. This area builds it up this way. This area still builds it up this way.
How come F? Hold on, F is not like that though. If that's a point charge, right? It's Coulomb's law.
Okay,
Right?
let's go back to the beginning.
Okay.
In the beginning, we said that there is a ring of charge and that this ring is huge and we're going to confine ourselves towards the center of the ring. And that's where this thing was just going to go back and forth and the force would have a slope like this.
Yeah.
You know from previous work that the force graph really looks like this, doesn't it? But we're confining ourselves to this part where it's linear.
Oh, I thought you were talking about like with that example right here.
That's my lousy, crappy diagram.
Okay.
This is the charged particle at the center of the ring. This is the charged particle at maximum displacement. And the ring is huge out here.
Gotcha.
Okay, sorry about that. So does everybody get what I'm trying to say? Is that this is, you know, the PE, we already used the formula. It's 1/2 kx squared. So if x is positive or negative. So that means this graph is going to, and I'm going to change the color. The graph for potential energy is going to have to curve up, reach some sort of maximum, and it's going to stay there for a while. Now remember, this is a graph versus time, not x. So once it's at maximum potential energy, it stays there for a moment, then it comes back down. It's curving. So you need to know what a potential energy graph looks like for a simple harmonic motion oscillator. The potential energy is at a minimum at the equilibrium position. Where is the kinetic energy at a maximum?
Equilibrium.
So that means at the same point, I'm going to be up here with my kinetic energy. And what's going to happen? You've seen this before, right? And what's the total energy going to look like?
Mm-hmm.
So at any point, you get the same total energy. Now, if I throw in the magnetic field there, it may change the graph slightly depending on how the path ends up working out. If the path ends up going in a loop, then there'll be a little bit of kinetic energy at the top of this curve. You follow me? No?
Mm-hmm.
Okay. I think it's kind of interesting to think what's going to happen when the particle starts to come back. As the particle comes back, the velocity is in the other direction and there will be a force, a magnetic force this way. So this thing is going to curve up this way, and then on the way back, it's going to have to curve the other way. What do you think? All right, let's get to the computer program.
Mr. Goodman, for C, why can't FB do work?
Okay, the force, the magnetic force is always perpendicular to the displacement at any moment in time. Let me clear this off. I'll show you what I mean. Oh, I can't clear off somebody else's stuff? Oh, yes, I can. Oh, I see. Clear everybody. I didn't clear the right thing. Anyway, here we go. Here's the particle. Here's the velocity. And here is the magnetic force. The displacement is perpendicular to the force. So work is force times velocity parallel, right?
Yeah.
So what if this velocity was actually in this direction?
Big component.
Then I would take the components of the velocity. This is the component that's perpendicular to, actually, what am I trying to say? No, that's not what I want. The B field is into the board, isn't it? That's funny. You realize that both velocities would be perpendicular to the B field?
Yeah. I see. Yeah.
Okay. So this velocity and this velocity, you would just use this velocity and say the B field is going into the board and the magnetic force would be in this direction. But that's my point anyway, that the B force will always be perpendicular to that velocity. Hello?
Yeah.
Okay. Now that doesn't mean it can't change the trajectory of the particle, because we know it can make this thing curve. So let me go get my computer program up and you'll get a kick out of seeing this thing. I hope. I got to get rid of my diagram. Okay. Let's hope it runs. Hooray. Sometimes this thing gives me an error because of what other programs have been running. All right. Here it goes. Hey, did I share my screen? Can you see this?
Yeah.
Yeah.
Okay, good. I modified the computer program that I used to generate that other AP open-ended problem that I gave you, where the particle was in the Earth's gravitational field. Here's the particle. It's going to have a velocity in this direction. Oh, for crying out loud. Hey, guys. I think it says on the paper that the particle's a negative charge, doesn't it?
Yeah.
Did we screw up our free body diagrams then?
I don't think so.
No.
I don't get it. If the velocity is positive into the right, then I got to put my thumb to the left.
Oh.
Can you guys look at that again? I think we put our thumb to the right. I erased all my work, so I don't have it here.
Yeah, you're right. It'll go down.
Did everybody hear that?
Yeah.
Our energy graph would stay the same, right?
Yeah.
Yeah. Energy won't change, but the I think our free body diagrams are upside down because we forgot that it's a negative particle, and that means you put your thumb to the left, and your fingers still go into the paper, though. Hard to believe. Oh, well. Okay, let's watch this particle go. You ready? Is anybody watching?
Mm-hmm.
Okay,
Let's go.
one person. Here it goes. Okay, how the hell did that thing curve up? Well,
Is it
do you think it's pretty?
because it's a positive in your in the program? Because everything's positive?
It's possible that my B field is coming out of the paper in the program. You're right. That could be it. Or the particle's positive. I will go back and check. But did you like this?
It's pretty.
I loved it. When this thing burst onto the screen, I said, "Ah, boy, I love this." What do you think of the graphs?
That's good.
Isn't that what we were saying?
Mm-hmm.
So
There's
which
a little
one is
bit of
kinetic
error.
energy and which one's potential energy?
The red one is kinetic, the blue is
Yeah.
potential.
Yep. Okay, let me go to my program and see if I think it's my B field is actually going the other way. Where's my charges? No, Q is positive.
That's
Q
it.
is positive. I'm going to make it negative. What do you think's going to happen?
I think that may not work. Oh, what? Okay.
That's, according to the
Same
free
thing.
body diagram, it should have curved down, right?
It automatically like changes the charge of the ring as well.
Oh, I see what you're saying. Oh, good point. Okay, here's how I wrote the program. I only put in a value for K for the oscillator. That's it.
Oh, okay. Okay.
So you got a really good point there. Well, now, do you notice very slightly how the kinetic energy doesn't quite come back to the bottom?
Mm-hmm.
That's because this thing does have a little velocity at the edge. Watch what happens if I make the B field stronger. There, my B field is 0.75. What did we put in this thing? Did I give a number? Yeah,
Yeah,
0.75.
0.75.
Okay. All right. Well, what if I made that, say, 7.5? Watch what happens.
It'll be a lot more exaggerated curve, I think.
You want to make a prediction? You think it's going to be straighter or more curvy?
Curvier.
I think it's going to be more curvy too.
Yeah.
But I still didn't expect that. Come on, ain't that cool?
I
Yeah.
like it.
So this thing kind of precesses around there. What the hell is up with my energy graphs?
It doesn't move all that far out, so like everything is smaller.
It doesn't slow down as much, correct?
It reminds me of an electron.
I guess it does. All the electrons I knew used to look like this. That was a joke. I think
And
that's
they
so
changed
cool. But I will tell you this. It apparently the magnetic field does affect the period, because look at this. Look how many waves there are here. Way more than before. So the period is shorter. All right. Let me challenge you. What do you think this would look like if the B field was 0? No B field. What's it going to look like?
Say circle. It looks like a circle.
Would it go around the border and just...
There's
It'll
no
go on the
magnetic
line.
force at all.
Yeah.
But there is still the electric charges around the whole thing.
It'll go back and forth.
There it goes, back and forth. Even though you can't see it, it's not animated here. It's still going. You can see the energy graphs, right?
Mm-hmm.
Now let's check the period. I'm going to count starting. I'm going to start here. 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles, a little more than 5.5 cycles. You get it?
5.75.
Now I'm going to go in here and put back the magnetic field to the point, the magnetic field to the 0.75. And let's see how many cycles we get in the same time.
More.
1, 2, 3, 4, 5. And before it finished with a little bit over here, right? Now it's up here. Hell, that's not even a quarter of a cycle more. It's very slight difference. So for all of this curvaceousness, or whatever I'm trying to say, the period is still pretty much the same. So if this thing goes out to here and back and out to here and back, it's not a hell of a lot different than with all these curves. Do you think that's cool?
Mm-hmm.
Now, it will if I make the magnetic field stronger and stronger, it does change because, like Dan was saying, the particle is prevented from reaching its maximum potential energy. And that will, of course, if it screws the whole thing up. I couldn't say it any more than that. I have to think about it, but it's definitely changing. Who thinks that's cool?
I liked it.
All right. Well, again, it's not so much saying, oh, we've learned a lot of physics today. It's more or less getting the experience, building up those mental calluses, so then when they show you something different, you're not panicking. You're saying, oh, this is what we've been doing. Everything looks different all the time. Does anybody have any questions they'd like to ask?
I'm good.
Hold on, don't go anywhere. Now I'm looking at this thing and I see that there's people. 3, 6, okay. Matthew, are you still there?
Yeah.
Did you
Hey.
find this interesting? Don't you want to say something?
Yeah, this was really. I actually think this was pretty cool with the seeing like a different way with magnetism and electricity, like how they
Yeah.
can be combined.
Matthew, now I'm going to have to give you extra credit because you're saying something. John, can you say something to me?
I liked this. It was actually pretty cool. Like with the pattern that when it makes with the magnetic field.
Well, if you think that's cool, would you be interested in trying one more thing before we end this session?
Sure.
Thank you. All right, let me change something. I'm going to move the initial, whoops. Watch what I do now. Instead of giving this thing an initial velocity, I gave it an initial velocity of 20. I'm going to give it an initial velocity of 0. And I'm going to have the original X value here not be 0. What was our maximum displacement? Does anybody remember?
.24 meters.
Okay, I'll make it 5. Okay. So we're going to start it off at 5 meters and we're going to see what it looks like now. Okay. It's, wow, 5 meters is not very far. Hey, was that the maximum displacement from the first part or the second part?
That was the first.
Okay, because when you double the velocity, we should have doubled our displacement. Nonetheless, I'll start it off right here. What do you think is going to happen? Which way will this particle want to go?
Left.
To the left. Somebody, whoever said that, thank you. Will it have a magnetic field on it now?
At the beginning, no.
No, because there's no velocity. So if it's going to go to the left, that means the positive motion is to the right.
Mm-hmm.
Eventually, this thing's going to gain a velocity. So which way will it tend to curve? It's moving to the left. Will it curve up or down?
Upwards.
It should. Ready to see?
Yeah.
Huh?
This is so damn exciting. Why did
Man,
it
look
do
at that data.
What did I do wrong? I gave it an initial position. Boy, how anticlimactic.
K is just small, maybe? I don't know.
I don't get it. Oh, how embarrassing. Shoot. I was doing this before and I was changing everything and it was really cool. All right, I'm going to make this bigger. I'm going to make it 15. See, you know what X naught is? Oh, I know what I did. I know what I did. X naught is supposed, this is wrong. X naught is supposed to be the position of the equilibrium. And I just made the X be equal to the position of the equilibrium. You follow what I'm saying?
Oh, okay. Okay.
No good. No can-do'sville.
Mm-hmm.
Hey, did any of you guys ever say no can-do'sville, baby doll?
What?
Kids were saying it at MIT. No can-do'sville, baby doll.
I'm not going there, so
Yeah, I think it's from a movie. All right,
unless I haven't earned it.
don't worry. We got bigger things. We're gonna write charged particles in motion stuff. Where am I going here? Where am I going? Alt R. Here we go. Here it comes. Ready?
What? Whoa!
Yeah. Tell me
Wait,
playing
what?
the simulations isn't fun. This is so damn cool. I just put it at the equilibrium position. The behavior of the particle to get to here affects the pattern. Because this thing came from here. Originally, it was coming from here and had a velocity, so it starts curving. Apparently, that affected the pattern.
Mm-hmm.
Yeah, huh? Now tell me you don't want to play with something like this.
Yeah, can we
You
make
want to
this Star
send? You want to
David?
send us the code?
Well, you know what? I could send you the code, and you can
You
play
want
with
us
it.
to make
That's
one,
like-
don't you?
You would probably have some fun. If you wanted to get on later, we talked about programming before. I can show you some stuff on this, and then you could say, "Hey, look, I did it myself." Okay, I think that would be. I would rather do that first. But if it really gets, you get stuck, then I'll send you everything I got. I don't care. Hold on, I want to change I'm going to make this just a. Can we make the time go on longer?
You're gonna have to do another, make another.
I gotta find where I put the time in. No, I didn't. Oh, look what I did. This is not a good way of writing the program. I'll make it go 10 times as long. Let's see what happens. Do you think it's going to line right back up again?
Oh, it just missed it.
No, it's doing another cycle now. Oh, that is cool.
I'm gonna put these on the physics shirts.
Yeah, we could. Could you imagine an AP exam where they say trace the path of the particle? And this is
I'd
what you're
cry.
gonna do. Oh my gosh, tell me it's gonna, it did! It's repeating now. Holy smokes, that is cool. It looks like we're looking into the center of a wicker basket that forms like a cone. It's a
Is it
black hole.
pointing up or down?
Oh, that's for us to decide, isn't it? Okay, kids. Well, I really have enjoyed this. I hope you've enjoyed it as much as I've enjoyed it. So you know what to do. Take some pictures, send them to me, and we'll say, hey, we had a good class.
Where do we send them to?
Teams.
Teams, okay.
And I think I said it on Teams. I might not have yet. Well, you'll see when we do it. Does anybody have anything else to say? Because all I want to do is give you the best that we can do under the current circumstances. Is there anybody sitting at home saying, I really wish I could do this or that? You can always email me, okay?
I want to know. I want to go outside.
Well, did anybody see the moon and Venus last night?
No.
Oh, baby. I'm going to share my whiteboard. See, now I'm going to bore the hell out of you. I had a good thing going. I can't leave well enough alone. Look, I'm going to show you what I saw. I hope you like it. This is the horizon. I'm looking over here towards the west. Venus was here. The sun had set. And the moon was here. And it was crescent. And the moon was lit up by the sunlight. It's pointed this way. You get it?
Mm-hmm.
I really wished it was clear the night before because the moon would have been closer. There are times when the moon is really close because the moon is going around the earth and it's going to go around like this. So in another month, we're a little less, we're going to see the moon really close to Venus. Venus in another month may make the curve and start coming back. Maybe not for another 2 months. I don't know. But certainly in the summertime, we're going to see Venus a lot closer to the horizon. In which case, you get out your telescope, and that's when you're going to see Venus with its phase as well. And that's going to be cool. All righty, guys. Time for me to go get something to drink.